Okay, so in a previous video I talked about some of my opinions on where 17.5 stock buggy should be headed in my view, and how we can embrace the diversity in approaches towards stock buggy strategy, and essentially allow that by limiting the total energy budget or the total charge capacity budget in a battery. So in that video I talked about having manufacturers make batteries of a specific capacity, like 1200 milliamp hours or 1300 milliamp hours or whatever, something that will like just barely make say a 6-minute main or something like that. But that's just one approach. It's, say, a relatively simple approach that would technically solve the problem. But a fair criticism of that is that it would require racers to constantly have to buy new batteries, because over time batteries degrade, their charge capacity degrades over time. The discharge curve is not the same for a small capacity battery as it is for a large capacity battery over a certain amount of charge. So really a better way to handle this, if you want to maintain a charge budget, if you will, for stock buggy racing, so that way you can, again, make outlaw motors legal, and you can make boost legal and all of that, and the only criteria is you have to basically finish the race within a certain milliamp hours of budget. A better way to track this is through the electronics themselves, through the speed controller. Okay, and so I'm going to show you some basic electrical engineering here that would essentially enable building a circuit that does this kind of functionality in a speed control unit. So when you turn on your blinky mode in a speed control, it basically sets it into this mode, and with some extra circuitry that's not shown here, you can basically define a capacity limit, and then the speed control itself will essentially like go into limp mode or something like that, or just shut off entirely once you consume too much charge. So that would allow you to run your existing batteries that have 4,000 or 5,000 milliamp hours and only use, say, 1,200 milliamp hours of capacity. Which is interesting because, again, like discharge curves are more stable over time. Like the voltage versus time for a large capacity battery is much flatter than it is for a small capacity battery. So you can actually leverage large capacity batteries to give you more performance over that 1,200 milliamp hour discharge than with a small capacity battery. So that's like another trick you can play. But anyway, how exactly could this work in a speed control? So here is a very, 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 very basic circuit of how a speed control works. So you have a motor, assuming a DC motor here, but really an AC motor would be like 3-phase with 3 resistors and a whole bunch of driving circuits. But basically you have a motor of some resistance that's driven by a transistor. Now this particular case is a pull-down case, which means I have an NMOS transistor here, and the pull-up network, if you will, is the resistance of the motor. The battery is, battery voltage connects to the motor, and then it drives down through the transistor. So as I apply a signal to this transistor gate, I'm turning this transistor on or off, and that allows me to throttle current through the motor. Okay, so what I would want to do is to be able to measure that current and essentially record that in memory in my speed control. And current is coulombs per second. So if I multiply that current by time, then eventually I get coulombs, which is also in different units milliamp hours. So if I'm recording my integrated charge over time, then once I reach a threshold amount of charge, I can shut the speed control off. So how would you do that? Well, the way you measure current is essentially by putting a resistor in series with the circuit path. And if you have basically that gives you 2 internal node voltages. You have a voltage here, we call it V internal 1, and a voltage here, we call it V internal 2. And the difference between these two, we'll call it delta V internal. Okay? And you can, if you know this reference resistance, if it's a known value and you can control it statistically, so that way from the speed control to speed control, lot to lot, you have the same exact resistance, then all you really need to do is measure the voltage drop. Knowing the reference resistance, you can infer the current. Okay? And then the trick here, the reason why you'll put a reference resistance here rather than just measure the internal voltage here and the difference between that voltage and your battery voltage, is because the motor resistance itself can vary. The motor gets very hot, or it can get very hot, and as it gets hot, the resistance of that wire in the motor can change. And so you have no specific reference resistance that you can rely on in the motor. And for the transistor, the resistance of the transistor depends on your input voltage to the gate, so you can't rely on that either. So it's easier to put a small reference resistance in here that is independent of voltage or temperature, or at least isn't exposed to the temperature of the motor, and say it's more stable over time, that you can use to infer a current. Now the thing is, because this resistance is in series with your whole path, if I'm drawing, say, 100 amps of current, I mean, that's a really high amount. Say I'm drawing 50 amps of current, and this is a 1 ohm resistor, I'm going to drop 50 volts across that resistor. But my battery is only 8.4 volts. So this resistance has to be a very, very low resistance, right? Maybe, I figure, like, your first order, less than 1 milliohm. Okay, so that way, at a 100 amp draw, at 1 milliohm resistance, the voltage drop here is about 0.1 volts. Okay, so that would be like your maximum voltage drop, minimal implications to the total supply voltage that you can drop across this motor. Okay, but the problem there is now, precisely because we want a small voltage drop here in order to not suck away too much power from the motor itself, we have to amplify this voltage externally so we get a usable signal. Okay, so we need to connect these internal node voltages to an amplifier. An amplifier is really just two inverters in series, okay? And then we measure an output voltage, and that's an amplified multiple of this delta V int, okay? So basically the equation would go, your reference current that you're calculating, you're back calculating, is the output voltage divided by the gain of the amplifier, right? So the gain could be 5x, 10x, whatever, multiplied by the reference resistance. So this is a known quantity. This is a known quantity that you design this to. And so all you're doing is you're essentially treating V out as the variable, and then you're solving for the reference current. Okay? Now, once you have that, then you can plot your reference current, or V out over A times RF, versus time. Right? So as I'm applying throttle and applying brake and I'm running a lap, I'm using different amounts of current at different points in time throughout the race. Okay? And what I want to be able to do, ideally, to get a perfect solution, I would integrate all of this function over time. And the problem is, applying a perfect integral to a function that is unpredictable is really complex. It basically requires a lot of regression fitting, best fit model stuff, complex circuitry that adds to power consumption that you don't really need. Like, you can simplify this dramatically with a Riemann sum. If you know calculus, if you take in calculus 2, Riemann sum is the introduction to an integral. And it's basically a numerical way to find an integral to a function. And it works really well if you have a very high resolution, right? You get very close to what the actual integral is. So if you can integrate, this current versus time, that's going to give you charge. And so then you could plot charge versus time, and then you're using more and more charge over time as you're consuming battery power, and then eventually you're going to reach some threshold charge. And so you build all of this into your microcontroller in your speed control to basically log, infer the calculated current over time, and then put that into, a memory bank that basically logs charge over time, and then once that charge crosses the threshold, then the speed control shuts off or goes into limp mode or something like that. So then you can have settings in your speed control to define what that setting must be, what that threshold charge must be. Okay, so if different tracks have different settings for threshold charge that they want to unilaterally define on their own, say, this track over here is going to run a 10-minute main, and so, 1200 milliamp hours isn't enough. We're going to give you an 1800 milliamp hour budget. You just plug that into your speed control and you're good to go. But if you want, say, if you're running a Roar legal race and those mains are sanctioned to, say 6 minutes or something, they might have their own universal specification for what the charge limit should be. And so there might be a special blinky mode where it's a green blinky light or something like that, that tells you this is the Roar legal, setting for the speed control for a charge limited race, right? And then you could have a red blinky light that has a custom setting, right? So you can play all those kinds of games. So this is something you can do within the electronics of the speed control. If you have the right microcontroller and the right programming and a little bit of extra circuitry, it is very possible to design a speed control, additional set of systems to that speed control to log charge, right, over time. And maybe they already do that. It's just not an actual like feature that's used for the end user. But you can do this. Okay, so anyway, just a little bit of basics in electrical engineering here on like how you might actually implement something like this. And I think if all the speed control manufacturers get on board with this, and if the sanctioning bodies get on board with this, then this would be, I think the most realistic way to advance stock buggy racing, again, so that you don't have to worry about regulating the specifics of the motor or the boost profiles or any of that stuff. Like, you just let people do what they want, as long as you're limiting the supply of charge. Then all they have to do is work within that uniform charge budget that's electronically measurable. And if you measure this at a high enough frequency, you're gonna very accurately measure that charge. And then so you could set up regulations for like what that measurement frequency has to be, so that all the speed controls are measuring, with the same methodology, right? So personally, I think this is the way to go, because it would make stock buggy a lot more exciting. So anyway, that's that, and thanks for watching.